Hi everyone, I'm Quan Tu from National Taiwan University, and today I will be presenting our work, COT-FM, which stands for Cluster-Wise Optimal Transport for Flow Matching. Let me start with a quick recap of what flow matching does. The goal is to learn a velocity field, basically a vector field over space and time that transports samples from a simple source distribution, like Gaussian here on the left, into a more complex target data distribution on the right. So at training time, we learn this velocity field, and at inference, we just start from a noise sample, follow this field by integrating an ODE, and end up with a sample from the target distribution. So all this modeling effort goes into learning a good velocity field. And here's a key observation that motivates a lot of recent works. The straightness of the trajectories really matters. On the left, the flows are curved. They bend on the way to the target. To sample from a curved flow, you need many small ODE steps, otherwise you drift off the curve. And on the right, the flows are really straight, so you can take much larger steps. In the extreme case, just one step, and still land in the right place. So straight path means faster sampling, and usually better quality at low depth counts. So the natural question is, how do we get straight path? The theoretical answer is optimal transport. The Western OT plan, shown in the formula here, pairs each source point at a target point to minimize the total squared transport cost. And it's a known result that this OT coupling induces straight vector field. So in theory, if we train on OT coupled pairs, we get straight flows for free. The catch is that coupling exact OT is really expensive and doesn't scale to the real world dataset. So in practice, prior methods like OT-CFM fall back to a batch-wise approximation, solving a small OT problem inside each mini batch as proxy for the global plan. Before getting into more OT-based approaches, let's see what happens without any coupling at all. Just random pairs of source and target, just random coupling, which is what usually flow matching does. So look at the zoom in on the right. You can see the lines cross each other heavily near the source. And when the model tries to learn one single velocity field consistent with all these cross paths, it averages out conflicting directions at each point. So this calls the curved path. One common workaround is batch OT, which is what OT-CFM does. The idea is really simple. Instead of solving global OT, just solve it within each mini batch. If you compare the two columns, batch OT does help a little bit. The line looks slightly cleaner rather than random coupling, but the improvement is still mostly local. Globally, the velocity field is still curved because each batch only sees a tiny slice of the data and cannot recover the true global pairing. You can see this in the bottom row on 2 moon. The generated samples doesn't match the true shape. The moons look smeared out, so generation quality stays limited. So the other direction is shortcut models like MinFlow. Instead of learning the velocity field, MinFlow learns the average velocity over a time interval, which lets you take bigger steps at inference. But the underlying it built on, just MinFlow built on it on top of, is still the same curved one. In the rightmost column and zooming, you can see the trajectory is still the trajectory near the source still spread in all directions, just like random coupling. So both directions, like batch OT and shortcut models, share the same bottleneck. The velocity field itself is still curved, and they work around it rather than fix it. This brings a key observation behind our work. Real-world data isn't structureless. Yeah, it naturally has cluster structure. Image dataset has semantic categories like dry grass, lifeboat, bookcase, and so on. So even without labels, we can use k-means to recover meaningful clusters from raw images, just showing on the right. So our idea is really simple. Instead of one global Gaussian as the source, we cluster the data and give each cluster its own source distribution. This way, the velocity field from each source to its target becomes more and more aligned, and the paths are naturally straighter. So here's how it works. We take a pre-trained flow matching model and reverse the ODE to map each data point back to noise space. For each cluster, we collect the reversed noise samples and fit an isotropic Gaussian. Then with each cluster, we run global OT to get better couplings and fine-tune with the flow matching loss. We automate this for around like 2 rounds and it converges. At inference, we sample a cluster index proportional to cluster size, draw noise from the matching Gaussian, and run the forward ODE just like flow matching does. And let's look at the result. On the left, we're showing one-step generation, generating an image in a single ODE step. You can see rectify flow and OTCFM produce essentially blurry blobs at one step. And adding COT-FM on top of rectify flow really gets recognizable shapes. But rectify flow plus COT-FM gives the cleanest and most comprehensive outputs. The takeaway is that COT-FM is a drop-in improvement that helps across multiple base models like rectify flow or mean flow, both the few step and many steps region. We also tested COT-FM on Libero, a standard manipulation benchmark in robotics. Here, flow matching models learn the action policy. Given a visual observation, it generates an action sequence. So on the left is flower, a recent flow-based policy. On the right is our COT-FM on the same task, using only one step, ODE. So as you can see the video, COT-FM completes the task while flower fails. This shows the benefit of straighter flows isn't limited to image generation. It transfers to policy learning, where inference speed really matters for real-time control. And here are our main quantitative results across benchmarks. And thanks for your listening.